So now that we've learned about exponential and logistic growth and kind of the biological implications of both types of growth, the next thing that we're going to explore is how do we model it? And what I mean by modeling is in the future, after 5 generations, how many organisms are there for both exponential and logistic growth? And we can do this with actually a very easy set of equations. And so yes, it's going to use math, but it's basic algebra. All we are doing is adding, subtracting, and multiplying. I guess I'm dividing too, but that's it. And so when we model something, you've actually worked with models before. If you have ever done a regression where you're fitting a line of best fit, you get an equation for that line and you can make predictions about the future. If you plug in a different x value, you can get a new y. Well, it's kind of similar here. And although our equations will look quite a bit different, the goal is the same, is can we forecast what the future would look like based on the type of population that's happening. So the first one we'll talk about is exponential growth. And right in the middle of this slide is the exponential growth equation. It's defined in the sentence before it, but I'm going to break it down. So this first term is delta n. So delta, this Greek symbol in math refers to change. So we have delta n over delta t. So it's a change in n. N is pretty much always in biology referring to number of individuals. So the change in number of individuals over a change in time. And typically what we're going to see the most when we're talking about change in time is generations. So we're not going to plug in 10 years. We're not going to plug in some time. What we just mean is over a time period, typically after 1 generation, what was our change in individuals? Now, it's very easy to be like, ooh, I need to solve for n, or I need to solve for t. We solve for, oh goodness, we solve for that whole thing. We solve for dn dt. Whatever number we get, so let's say we do this formula, we get dn over dt equals 100. What we're saying is that this population changed over this period of time. And in this case, this is positive 100. So we're saying that it increased by 100 individuals. So we solve for dn dt. We don't break that down at all. That stays together. Now for exponential growth, the way we find this dn dt is we take the r. We've seen the r before. Remember, this is the birth rate minus the death rate. And then we simply just multiply it by the number of individuals there are. That's it. So on the next slide, we're going to break down the problem that you see here. This problem is also written down in the population growth worksheet that accompanies this video. It doesn't have anything new or special on there. It's essentially just giving you space to work on these different problems. So I have a starting population of 100 diatoms, and they're exhibiting exponential growth. Each generation, 45 out of 50 diatoms are produced, and 1 diatom out of 40 die. And then my question for you, why I want to use this population model, is how many diatoms are there at the start of the 5th generation? And so we need this whole equation, but we can't just go ahead and start, oh, what's the 5th generation? We need to figure out where to start. Well, if we look at our equation, we're given n, right? I have a starting population of 100 diatoms. So what I currently need is this r. And we know how to figure out r. We know if we take the birth rate, which is 45 out of 50, which equals 0.9, and if we take the death rate, 1 out of 40, which equals 0.025, I can solve for r. And so that's what you guys should do. So I have 0.9 minus 0.025, which equals equals 0.875. And definitely keep these decimal places for the R value, decimal places matter. I would say for R, for future problems, R do 3 decimal places. Because we might be working with huge populations that are, say, 1 million individuals, and that 1 decimal place in R will make a huge difference in your values. So for R, really important to have that as exact as possible. The other numbers, not so much. We'll talk about that more in a moment. But R, let's say 3 decimal places, if you have them. If your R value is 0.6, don't be like, I'm going to do 0.600 in your calculator. It's exactly the same. So we now have everything that we need for our equation. We have the R, 0.875. We have the N, which is 100. And now very simply, we just solve for dn dt. But the thing is the problem said at the start of the 5th generation. And it would be lovely if we could just plug in a 5 somewhere in here. But we can't. We actually have to figure out generation after generation after generation. So this next slide, all I've done is I've written that same prompt at the top. I've reminded you of the equation. I'm going to go ahead and right over here, we already solved that R equals 0.875. And here I have a data table set up. You can set up your data table similarly to mine. I purposely put more columns than I need just so I can show you every single step. After we do an example together in the future, you might simplify your table a little bit, which is totally fine. So what you see here is in this table, I have 5 generations. Again, there's no quick way, there's no shortcut to just automatically solve for the 5th generation. You have to go generation by generation by generation. So what I'm going to do is at any point pause if you want to copy down this table and then just restart this video. I'm going to go through the first 2 rows together. I'm going to show all my work. I'm going to put in everything. And then on the next slide, I actually have all the answers for you so that you can compare your numbers. So I have my generation column. I have N, so the number of individuals. I have my dn over dt equals r times n equation, or simply, this is where I'm going to do r times n. And then I have my new n. What is my new population? So let's start with the first generation. So we are given 100 diatoms. Now our next step is to do r times n. So r again was 0.875. My n is 100, so I'm going to times it by 100. And this equals 87.5. I will say for this column, actually for all these columns, 1 decimal point. That's all you need. Honestly, you don't really need that. Now you might argue, well, these are organisms. We shouldn't have decimal points at all. Like we should be rounding these because these are actual organisms. The reason we don't is we're now in a mathematical model. We are now in this beautiful, perfect world where a population is beautifully growing exponentially. We're not in biology anymore. Math doesn't care about whole numbers or not. So I expect you to keep decimal places, but just 1 decimal place is fine. Honestly, you could probably get away with not, but just keep 1 decimal place and just know that that's the reason why we're not rounding, is because we're in a mathematical model now, not in the biological world. We're using math to kind of help explain or predict the biological world. Anyway, so we got this 87.5. Now, this is not our new population. Remember, 87.5 is the change in population over time, in this case, over 1 generation. So if my population changed by positive 87.5, what's my new population? And this is just looking at N. I had 100 individuals. I just now added 87.5 individuals. So I very simply just add these together. So 100 plus 87.5 is 187.5. So at the beginning of my first generation, I had 100 individuals. At the end of my first generation, I had 187.5 individuals. This number, 187.5, just carries on down. So at the start of my second generation, I have 187.5 individuals. I'm going to do this math again. So r times n, 0.875. R is not changing. R is constant. Times, now my n has changed. I don't have 100 individuals anymore. I have 187.5 individuals. If I multiply that out, and I've already cheated and I've already done it, I get something like 164.1. Now my numbers might be different. Excuse me, that one might be the same, but I will say I did all of these in Excel, and you'll see that on the next page. If your numbers are a little off, that's fine. Off by a couple, that's just rounding differences. But if you're seeing huge differences, there might be an error. So again, here's our r times our new n is 164. Remember, 164 is my change. It's positive, which means I added 164 individuals. So I had 187. I'm going to add 164, and this leaves me with 351.6. So at the end of my second generation, I have 351 individuals, which is also the same number as the start of my third generation. So I'm not going to keep writing out the steps. The steps are the same generation after generation. What I'd like you to do is pause this video here and work on the rest of this table before switching and continuing on with this video, because the next slide has all the answers. So go ahead and pause here. All right, so let's check if your answers are correct. So you can see the first two rows are the same first two rows that I walked through, and then I've now populated the other three rows. Again, if your numbers are off by, say, 10, maybe even 20, that's fine. It's rounding. I used Excel to come up with this answer key, and Excel keeps all the decimal places, so I just rounded. But you probably rounded a number and then used it in the math, and then rounded the number and then used it in the math. So I expect yours to be different. Now, that's great that you've made this whole table, but keep in mind, I gave you a question. Be sure you answer that question. So the question is, how many diatoms are at the start of the fifth generation? So if you're taking a quiz or a test and I ask you this, be sure to answer that question. Don't give me this whole table, because this table just tells me, hey, you can plug in the numbers, but can you answer the question? Now, simply, you could just circle it, and that's totally fine. So the question is, how many are at the start of the fifth generation? I have 1,236 individuals at the start of the next generation. So one last thing that I'd like you to do is within your notes somewhere, create a graph of this. So plot the generation, so 1, 2, 3, 4, and 5 on your x-axis, and then plot n, so this n, on your y-axis. We're going to do logistic growth in just a moment with the same exact data, and your graph is going to show you this pretty nice difference between your logistic growth and your exponential growth. So go ahead, pause here, take some time to make these graphs so that you're really plugging in like, oh, wow, I just created this beautiful exponential curve. I've created this J curve with data that I solved myself. You can kind of make those connections. So again, go ahead, pause here, and work on that graph.